Okay, yeah, so welcome to the last lecture in this series. Yesterday, in some sense, we kind of reached a nice point because we, just to remind you, we had gone over a few different kinds of models of random graphs or randomness-ish graphs, which produced different ensembles of graphs. And some of them had properties where their path lengths were small, some had properties where their clustering coefficient was large, and so on. And I tried to give you some comparison with real networks. But it turns out that none of the three different things that we talked about, Erdos-Renyi, Watt-Strogatz, or preferential attachment, actually explained everything. And in a sense, one direction in which the field progressed from that point onwards was to try and find more sophisticated models that actually reproduce some of the features of all the features of the real networks. And in some ways, what happened was that the field itself, in that sense, fragmented towards looking at different particular real networks and looking at models that were more focused to specific networks. So if somebody was interested in the internet and reproducing those features, then they'd be looking at models that would be getting close to that. But those models may not produce the features that, say, an ecosystem model produces. So in some sense, all the simplest models that were kind of universal, or at least you could hope that perhaps they have some universal applicability, are the kinds of models we have already gone through. The field went on from there to start producing more complicated models. I don't actually want to do that and get into more specifics. Again, what I'll try and do is perhaps put up some references. I'll give to Sanjib or Abhishek to put up references for specific fields where people have looked at more models of random networks that are more suited towards specific sub-areas. What I wanted to do instead today is to go back to Erdos-Renyi, because there is one particular feature of that ensemble which we have not talked about and is a very, very interesting result and has applications across, not just in Erdos-Renyi, but in all sorts of random graph models. And it's also something that comes up because it relates to an assumption we made, that I made in many of the arguments I was making, which I kind of swept under the rug. But it's come up in various places in questions you have asked in the tutorial. And it's to do with the issue of connectivity. So far, just to remind you, we said that for Erdos-Renyi networks, the diameter went as something like log n by log k, where k was the average degree of the nodes. And we were looking in some limit where n goes to infinity, p goes to 0 in such a way that pn is a constant and is this average degree, right? And the kind of hand-waving argument I had made was that you start with a node, this will have on average k neighbors, and these will then have on average k more neighbors, and so on, and you can keep going out from here and seeing how you spread as you take steps through the network. And you can make a hand-waving argument for log n through this, right? The big assumption that underlies this argument is that you can actually reach the whole network, right? We discussed this in the tutorial yesterday when somebody was asking about how you actually calculate diameter in a real situation. And there is always this problem if the graph is disconnected, consists of two disconnected subgraphs. Technically, the diameter is infinity because there are no paths from some nodes to some other nodes. So if you have a graph that looks like that, there is no path from this node to this node. So in some sense, the shortest path from that node to that node is infinitely long. And the diameter is infinitely long. So so in some sense, what we have not discussed so far is what happens as k changes. We looked at this limit and we've said k is constant, the average degree is constant, but clearly that's a parameter. The average degree could be really small or it could be very large. Clearly, if the average degree is much, much less than 1, then you will have a network where there are very few links, right? If the average degree is much less than 1, it means most nodes have no links. And some one node here and there will have a link. So it does seem pretty obvious that as this parameter becomes very small, less than 1, you are likely to have a disconnected graph. Somebody asked the question, can you have a sparse network and yet connect it? And those are the kinds of questions we want to address today. So what I want to talk about is in the Erdős-Renyi network, we'll stick to this situation. We'll stick to the limit where n goes to infinity, p goes to 0, but with this constant. But we will investigate what happens for different values of k. Okay? And there is a very interesting result here because essentially, I don't think it's too much to give it away before we get into the calculations. The point is that you go very rapidly from a disconnected network to a fully connected network as you change k. And in particular, a very interesting thing happens as k crosses 1. So below 1, typically, I'm just giving you the answer, and we'll do a little calculation to try and justify what I'm going to say now. You typically have the graph consisting of many, many small disconnected clusters. Most of them are trees. They don't even have cycles. So there are very few situations where even something like this would occur, though those do occur sometimes as you get close to 1. But generally, they're all many disconnected trees. Here, as you cross to that side, here what happens is you get a graph which has a very interesting property, and an infinite number of nodes get connected into one cluster. Okay, so remember we are talking about the n going to infinity limit. So what I'm saying is in this part below 1, all clusters are finite. Some of size 1, some of size 2. So this is like a 2 cluster. This would be what I would call a 1 cluster. 3 clusters could be like that, or triangles, things like that. Essentially, in this region, your graph will consist of a bunch of disconnected clusters of various finite sizes. There will be no cluster that actually contains an infinite number of nodes in that limit. On this side, on the other hand, there is going to be one cluster which will actually have infinite number of nodes. Okay? So this has many hallmarks of a phase transition, and that's one of the reasons why it's kind of sensible to talk about this in a stat phys school. For instance, if you plotted the fractional size of this giant component, it's called the giant component, this cluster which has infinite size, it actually goes something like this. So you can see there's a discontinuity here. Below this, the size of the giant component, or the largest cluster, is finite. So in the n going to infinity limit, any finite cluster, the fraction it occupies of the entire network is 0 in that limit. But from here onwards, there is actually a cluster of a finite size. So although, sorry, of an infinite size, so although it is infinite, it doesn't mean all the nodes are connected. That starts happening as you go further up. So eventually, asymptotically, as k goes to infinity, you of course, your giant component starts accreting more and more and more nodes, and eventually, at some point, you're so large that you start approaching very, very close to the entire size of the network, which is infinite. Okay? You can look at this in other kinds of things. You can look for the second moment of the cluster size distribution, right? These are the kinds of quantities that are analogous to, for instance, in other kinds of phase transitions you may be used to, like the Ising model or magnetization, right? You must have seen something like this. This is like the magnetization. What's the size of the domain in an infinite Ising model system? What is the largest domain that has all spins up, let's say, right? You know that at some point, there is a transition where that domain becomes infinite, right? Yes, are people familiar with this concept? You know in other kinds of transitions also, right? You know that, for instance, boiling water, people look at the size of the bubbles that are there. You know what below boiling point, what's the size of bubbles of water if you're heating water? What will that distribution look like? Any idea? Have you ever come across that concept? maybe for the icing model. What does it look like for the icing model? In the icing model, of course, below the critical temperature, you have no net magnetization, but you do have domains where spins are up, another domain where spins are down. What's the distribution of sizes of these? Anybody have a clue? No, the power law comes exactly here, right? What happens over here, so over here, the distribution of sizes is exponentially falling. So there is a characteristic scale. So if you're saying the size is something like exponential minus alpha, the probability of seeing a cluster of some size goes like this, then alpha sets a characteristic scale, right? At this point, you will indeed get a power law. Exactly at this point. So you will have something like 1 over s to the power some gamma. And beyond this, you will have, in the icing model, a giant cluster. An infinite set of spins that are all spin up and are connected, right? So if you're not familiar with that, don't worry. We are going to do more or less exactly the same thing, and we'll talk about exactly the same phenomena in these networks, in this networks context. So for those who are familiar, you can sort of understand what's going on. You can make an analogy to that. So what's going to happen is, in the networks picture, below k equals 1, there will be lots of disconnected clusters. And in fact, we will try to show that the sizes of these clusters are exponentially distributed. Over here, there is a giant component that comes up. And exactly at that transition point, there is in fact a power law. The size distribution is going to be a power law. Okay, so these are the kinds of results we want to get at. And this is very, very interesting, not just because Erdos-Renyi shows it, but this is, in its own way, the same kind of transition happens in many of the other models. Okay, we'll talk about, if there is time, we'll talk about it even in the context of the preferential attachment. There's a sort of analogous transition that happens. But essentially, it's very, very common in all sorts of models of random graphs or graph evolution, graph creation, growing graph models, where you start adding links that at some point, at a certain critical average degree, you go from a situation where the graph is very disconnected to one where it's all connected. And the point at which this transition happens in Erdos-Renyi is 1, but in other kinds of graph models, it may be at a different place. Okay? So this phenomenon is sort of it's in the Erdos-Renyi, we can actually do some calculations, show some of the things analytically, gain some intuition, but the phenomenon itself is not just restricted to Erdos-Renyi. It's true for a lot of graph models. So it's something you should always be thinking about in terms of graphs. And maybe this answers a little bit the question that somebody asked earlier. Can you have a sparse graph that is connected? Yes, for many, many graph models, like Erdos-Renyi, you can, because over here, in these regions, you are still very sparse. You still have only, you may have still only an order 1 or less than order 10 number of links per node. So that can be very small. Remember, we are talking about the n going to infinity limit. And yet, you can have these large, giant connected components. Okay? Okay, so let's actually get to some calculations here. And yes? Yes. Well, so of course, as this goes to infinity, indeed, in that limit, everyone has infinite number of connections. So that's the limit where it really approaches. But in practice, by the time you're already up to something like 5 or 6, a degree 5 or 6, even for n going to very, very large numbers like millions or more nodes, you will be so close that essentially in practice, if you were actually making these things on a computer, your giant component would have covered the whole network. Okay? All right. So any more questions about this? What I intend to do? Oh, sorry, I did start by saying, you can measure the second moment of the cluster sizes. And that actually shows a discontinuity. It goes something like that, goes off to infinite, shows a singularity, and then it comes down. So that's also characteristic. It's like, I guess susceptibility or some such thing. So these are, I just wanted to show those kinds of curves because some of you may be familiar with phase transitions in some contexts and may have seen certain kinds of discontinuities as being characteristic of the point at which a phase transition happens. So we're going to see this. Let's come back to that. Let's do a calculation first, get some of this, and then we'll talk about what kind of phase transition it is. Okay, any more questions? All right, so let's try and understand how this happens. So again, just like we did with the preferential attachment, I'm going to recast Erdos-Renyi graphs as a process in which a network is grown, rather than a process in which we just take, say, a certain number of links and just throw it down on a certain number of nodes. So we are going to think of a graph with n nodes. We are going to start with n nodes. And remember, in the end, we're always going to be thinking in the limit n goes to infinity, but wherever you need to, you can try to use your intuition for finite graphs and think about what will happen to as n goes to infinity. But remember that this kind of curves that I'm drawing really are for the n going to infinity limit. In the n not infinite limit, all of these will become a little smeared out. This infinity won't be infinity, it'll smooth out somewhere there. This will also smear out like this. But in the limit n going to infinity, that's what we're interested in. And we're interested in seeing these sharp discontinuities there. So we're going to start with this at time 0, n isolated nodes. And I'm going to add add links to this system at a rate n by 2 per unit time. In other words, the number of links is going to be, the number of links as a function of time is going to be n by 2t. And the reason I've chosen this is so that your degree, average degree, grows with time as just t. So it's just a particular normalization I'm choosing just so I can keep certain calculations simple. Is that clear? We are looking at undirected graphs. We're going to ignore self-loops, multiple edges, and so on. Similar arguments that I made for the preferential attachment work here. In effect, you don't have to explicitly exclude self-loops and multiple edges, because in the n going to infinity limit, that kind of thing won't happen anyway. But essentially, we're going to be adding links randomly. So every time we add a link, we are going to choose 2 random nodes, put in a link. And the rate per unit time that we're at, the rate at which we're adding, so we're going to be adding n by 2 per unit time. Is this clear? Is this connection clear? We talked a little about this yesterday in the preferential attachment case, right? The degree, every link adds 2 to the degree, right? Yeah? So your total degree is going to be 2 times L, and your average degree is going to be 2 times L divided by N. That's how you get this. Any confusion there? Because that's the starting point. Okay, so now imagine what happens to clusters of different sizes. So initially, some link will form here. So initially, everything was of a size 1. I'll call that a size 1 cluster, an isolated node. This is a size 2 cluster, okay? Over time, something else will happen. The number of size 2 clusters will grow. Maybe after a very long time, who knows, something else has happened. More complex structures have formed, okay? At some point, you can imagine, as links get added, clusters may join up to form a larger cluster. Indeed, that's happening right from the start. If you think of this as a size 1 cluster, a link connecting 2 size 1 clusters produced a size 2 cluster, right? So in general, you will get a size k cluster when you put a link between a size I cluster and a j cluster. This will give you that, provided k is equal to I plus j, right? So let's imagine at any given particular moment of time, there are that many clusters of size I. So I'm using capital X, or X, I, as the number of clusters that exist of size I. So initially, this is going to be 0 for I greater than 1, and some value n for I equals 1, right? And over time, the x1 will go down, x2 may go up, maybe later x2 may come down, x3, x4, x5 will start going up. Is that clear? So imagine, so this, what we're doing really is mapping this onto an aggregation problem. Aggregation problems have been studied in statistical physics forever. There are lots and lots of different systems where aggregation is the basic dynamics of the system. Okay, various kinds of clusters, monomers coming together to form larger n-mers, and you want to look at the size distribution of these. So what we want to understand is, what's the probability for something like this, an I cluster and a J cluster to come together and form a K cluster, right? Yes. K nodes, yeah. So when I say K cluster, it means it has K nodes. That's why K has to be I plus J, because simply, so this was a 3 cluster and a 2 cluster that came together by this link and formed an overall 5 cluster. Yeah, pretty straightforward so far, right? So we need to now ask, with this process that I told you about of randomly putting a link, what's the probability that an I cluster and a J cluster will come together to give you a K cluster? Right? So the first thing is, you have to pick one of the I clusters. You have to pick one of the nodes in that I cluster, right? That has to be one of the 2 random nodes picked. So that has a probability like this. Yes? And you have to pick a J cluster and one of the nodes in the J cluster. And since there are J nodes in the J cluster, we get something like this. Now, I made some assumptions here, but do you see that this is sort of a multiplication of 2 probabilities? So this is the number of clusters that exists of size I, and we have to pick any one of those nodes. So I multiplied by xi is the total number of nodes that are there in I clusters, size I clusters. And that fraction of the network is given by I xi divided by n, right? So essentially, we're saying at a given moment in time, at some time t, if you know, so technically I should call this xit, xjt, right? If you know the xi values, then this is an approximation of the probability that a new link will join an I cluster and a K cluster, and a J cluster, all right? Now I'm making some assumptions here, obviously, right? I'm assuming that there's no double, that you didn't pick 2 links from the same cluster, that you didn't, so I could have, for instance, if this was the situation, the 2 nodes I could have picked up randomly are this one and this one, right? That would be a case that would violate this kind of scenario. So there are terms I am throwing away here, and I'm not going to try and get too deep into that, except to say that all of those processes are second order and go away in the n going to infinity limit that we're interested in. So this is a pretty good, in fact, an exact assumption in the n going to infinity limit. In a finite case, this will not be exactly true. Correct. Correct. So most of the problem happens when I is equal to j. When I is not equal to j, it's fine. So there are some issues over time. Yeah. So okay, let's put it this way. The biggest issues in writing down in this approximation happen when it's the same cluster that's coming through. Okay. You do want to be a little careful there to make sure. So what would you do in a finite size situation? In a finite situation, if you had one cluster of size 2 and another cluster of size 2, and these were the only two clusters around, the chance that you would make a 4 cluster is not going to be 2 times 2. This is x of 2, right? x2 at time t, divided by 4 plus 2 times 2 divided by 4. It's not going to be this, because once you have picked a node here, you can only get a 4 cluster if you're going to pick one of these nodes. So you have to remove this from n. So the second one would be somehow you would remove the earlier cluster you have picked out, and you would not be looking at xj, you would be looking at xj minus 1. So there would be extra corrections that would come in there. My point is that don't worry about that too much. In the n going to infinity limit, all those terms do not matter. In the n going to infinity limit, this actually becomes exact. Okay? So essentially think that in a very, very large network where you have many clusters of all different sizes around, the chance that a link ends up between two different clusters is much, 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 much higher, and is really the only process you need to worry about, than a chance that then the finite size effects and the probability of sort of having picked a cluster of one size, you reduce the number of clusters of that size around. So what we're going to do, therefore, in this n going to infinity limit, I'm going to look at the following quantities. Instead of looking at the xi's, yes, you have one more question? Yeah. 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 So not quite. I mean, you're almost there, but not quite. It actually turns out that it's fine as long as k is a finite number that does not scale with n. So the problem happens is if you choose k, or this average k, to be a number that's proportional to n, then you will have a problem. Then you will have problems and you cannot write it like this. As long as k scales as anything less than n, log n would be fine. It still works out. But we are going to actually work in the limit where k is a finite number. So it may be a very large finite number, but it's still a finite number. And in that limit, so we are really working in this limit, where this is a constant that is independent of n. In this limit, all of this works out. But you're absolutely right that if you do a different sort of limit, where even this was going to infinity, then that would be a different situation entirely. Okay. So what I want to do is, instead of, I'm going to recast this in some new variables, where I will call Ci the following. I'm just defining this to be xi by n. And this is going to be all in the n going to infinity limit. So I'm going to assume that this is some kind of concentration-like variable, right? You're, instead of looking at the number of molecules, you're looking at the density of molecules or particles or something like that. So here we're looking at something akin to the density of clusters, except that the normalization is n. So remember that what this means is that summation kck is 1. So normally when you're, because I've chosen n, this is the number of nodes. And this is the number of, so this is the number of clusters of size I, and this is the number of nodes in the entire network. This quantity satisfies this relation. Is that clear? Sorry? It's a bit like that, exactly, but not quite. So here, just think about this is a quantity that's telling you about a snapshot. This is something that is a function of time. This is also a function of time. This tells you something about the cluster size distribution, certainly, right? But it's normalized in a certain way in order to get this. So it's something akin to the cluster size distribution. But it's the version of the cluster size distribution that makes sense in this limit. and that we can actually calculate things about. Okay? So now what I would like to do, just like we did with the preferential attachment, we were looking at actually the distribution of the distribution of the degrees. We were looking at the fractional number of nodes that have a certain number of that have a certain degree, right? You remember we were looking at nk, and then we were trying to write down something like a master equation for dnk by dt. We're going to try and do the same thing over here and write down a master equation. I want to keep some space here. So can I rub this out? Actually, maybe I'll just rub this out. I'll start here. So what we want to do is write down an equation for this. So how will the density of k clusters, size k clusters, change with time? Just like we did in the preferential attachment case, there will be some positive terms which will consist of clusters coming together to form a k cluster, and there'll be a negative term for the case where a k cluster joins with some other cluster and goes away, right? So I'm just going to write this down and then we can try to talk about this. So I'm going to sum over I and j, but such that I plus j is equal to k. And I'm going to write down I ci multiplied by j cj. And so I don't make a mistake, k ck. Okay? This is the stuff that's inside the sums. This is a different term. So these are the two terms that contribute to clusters of size k. Here you can see this is the term where two clusters of size I and j come together. This is the term we've seen before over here. I times ci multiplied by j times ci. This is the probability of those coming together. And I'm summing over all possible I and j such that I plus j is equal to k. Xid by I? No, I am defining ci as xi by n. That's why I can write, I'm taking this, which was the probability that the two clusters come together, and I'm able to write this in this form. If I defined it in a different way, if I defined it as xi by sum over xi or some such thing, you would not be able to write such a neat little equation. This would be different. Yes? Right. Yes. So, no, so indeed, it's, well, I mean, if you're thinking about a real process that does this, of course, but we are actually trying to build a network with a finite degree, but infinite size. So we actually do have to add infinite links. And we do have to add links at an infinite rate. So if you're implementing it on a computer, you will always have a finite size and everything is okay, you will be doing it. But indeed, in the limit n going to infinity, if you actually have an infinite network with a finite degree, average degree, there have to be infinite links. So since we are working in that limit, we do need to get in a finite time to get somewhere, we need to actually do this. So yeah, so think of this as, you can think of it as an unrealistic limit of, so think of it, how does the same thing work in, say, a thermodynamic system? It's because interactions and stuff and processes all happen in parallel. And if you have that many molecules in a room, it's not that the collisions here are waiting for collisions there. If there was a network-like system, which was really well described in this limit of n going to infinity, let's say it's the brain or something, which is growing, that links would be forming in parallel everywhere. So in a sense, what we're saying is that yes, the net rate, if you were looking at the total system and the rate of links going up, would be going to infinity. But In an infinite system, that can be from a local finite process. If every location in space, say in the brain, was creating a new neuron, you would get an infinite number of neurons in a finite time. So it's that kind of analogy we're making. Do people understand where this 1/2 comes from? It's to prevent double counting. Because I'm summing over all I and j, I will double count the number of cases where, say, so suppose I wanted to get a 1 cluster plus a 2 cluster gives a 3 cluster, right? I will go over I equals 1, I will hit it when I is equal to 1 and j is equal to 2, and also when j is equal to 1 and I is equal to 2. So this is simply taking care of that. Okay. Why does this term, this is now the term which is the loss term. So k clusters that are joining up with other clusters and disappearing from this quantity, because they're becoming larger clusters. Why does this not have, say, something like Cj or something? Yeah? So it's summed over. So implicitly, actually, you would do the same thing. You would do kck, I, ci, but you would sum over all possible i's. And we already know that the sum over i's, this one, because of the normalization we've chosen, is 1. So that's why this goes away. Is that clear? So you can try and play with this, actually. It's useful to sit, maybe yourself, and think about small clusters of size 1 and 2, and ask, think of a small network, and ask, is the combinatorics okay? What happens if I had a network like this, and that was combining with another network like this, where they're both 3? Then think about networks where you're looking at different sizes, and just check that this all works out. Okay? This is a master equation for this quantity, which is actually something that shows up in a lot of aggregation problems. In statistical physics, there are many aggregation problems that can be written like this, except that this term, in general, we have a term which is I, j, ci, cj. In general, this is not the case in aggregation, and you'll have some kind of kernel, this would be called a kernel, and ci, cj. There are many, many, many aggregation problems that take this form. And we are looking at a particular case, which is called the product kernel. But you can imagine lots of situations where this happens. So people study this for droplets aggregating together. People study this for chemical sort of networks where you have monomers. Monomers can come together to form dimers. Dimers can come together to form larger mers, and so on. And you want to know what's the distribution of at infinite time, what are you likely to see? Are you likely to see very large n-mers, or are you likely to see all finite n-mers, and so on? So there are lots of aggregation problems of this sort. We are looking at one special case because of the way we set up the addition of links. Because we set it up as random, and in this Erdos-Renyi type style approach, it became a particular case. If you think even of networks in a more general case, and we generalize the way the links come in, and you think of preferential attachment, you would change this. So you could do a very similar kind of calculation, but in preferential attachment kind of situations, but you would need something else over here. Right, somebody had a question? Did you have a question? Okay, fine, great. Yeah. Yes, so I am making the assumption that it's product, and the reason, so you mean this assumption? Or this assumption? Yes, so indeed writing this itself, forgetting about what this kernel was, but writing it in this form itself is already an approximation, and there are aggregation models where even that would not be correct. So there is an approximation here, and also an approximation in writing the kernel as I times j. So both approximations are there in this case. And in this case, they're justified by by this sort of random process by which the new link is added. The new link is added to a random pair of nodes. Okay? Okay, so now we need to try and solve this And I'll try and, just as we did, you'll see that often you end up using very similar kinds of approaches to very different problems, because the ways one goes about thinking about the solutions of this are very similar to the way we, for instance, thought about the other master equation we looked at yesterday for the degrees, for the preferential attachment case, right? So what did we do there? We started by getting some intuition about the first few. So let's think about dc1 d by dt. So this is a case where this term does not exist. The first term does not exist because there is no I and j that is 1 or larger than 1 that can, where two things can sum up to give you k equal to 1, right? I sums over 1 to infinity, j sums over 1 to infinity. There is no ij value which will give you I plus j is equal to 1. So the only term you have left is this, right? Everybody knows how to solve this? This is easy, right? So because we started with the initial condition that all nodes were isolated nodes, so that means initially the only clusters that were there were of size 1. This would basically be e to the minus t. So this is 1 multiplied by this because C1 of 0 is 1. Yeah, and so our initial condition, maybe I should just be more explicit, C1 0 is equal to 1 and CK 0 is equal to 0 for k greater than 1. So with this kind of initial condition, this is really simple. So let's try and figure out what happens with C2. What's the equation? Let me make sure I don't make a mistake here. So half, there is only one pair, right? This is going to be satisfied only for I is equal to 1 and j is equal to 1, right? So you will have C1 squared minus 2C2. Sure. I mean, yeah, because our cluster sizes are integers, right? So of course, you can only look at that. So what about this? If this term had not been there, this would be easy. You know it's the same kind of exponential. But because this term is there and we know this is exponential, this is e to the minus 2t, it's not so straightforward. But maybe you have actually solved an equation like this. Okay, I'm not going to solve it from scratch. I'm going to do what a lot of textbooks and people do if they already know the answer, which is to guess a solution and then make sure it works. So I'm going to postulate that this is some constant times t e to the minus 2t. It's not such a difficult guess, actually. If you worked with differential equations, this is one of the kinds of guesses you would make pretty soon. There is an e that comes here. Even if this term was not there, if this term was not there, you would actually expect C2 to go down as e to the minus 2t. So the fact that there's another e to the minus 2t gives you some indication that there should be an e to the minus 2t over there. But when you differentiate it, you need two terms to pop up, so something like that. So let's just make sure. So what will be the value of A? Let's just see. dc2 by dt is going to be what? A e to the minus 2t minus A 2t. Sorry, did I make a mistake? 2t e to the minus 2t. Is that correct? Yeah. So this, as we know, is 2c2. So this is minus 2c2 already. And this has to be half e to the minus 2t. So what we need is A to be equal to half. So this is solved by the following term. So C2 is equal to half t e to the minus 2t. And now we'll go and do one more. So here you'll start seeing the combinatorics start coming in, because now there are multiple ways of getting a 3 cluster. Yes, there's a question. No. Yeah, but that's fine. That's still okay, because there are two such, so there are two ways still to do it. So just think about a case where, so you have some case like this, right? You have two one clusters, and you're throwing down a link, and you're asking what's the rate at which you will. So since we are putting in links at rate n by 2t, essentially the rate at which you will build up a cluster like this will still end up being half. So the half will still come in. Okay, we can go back to this maybe in the tutorial and try and think about that, but you will find it'll work out. There are still two ways you still need to put in the half over there. Okay, so, so let's see. DC3. Well, this one you can guess. Now we've already got two, so you can try and guess the next one. But this is going to be something like this. It's going to come out, if I'm not mistaken, as something like this. And here you would get an e to the minus t from this, and you would get a t e to the minus 2t from this. And essentially what that leads you to for a solution for C3 is something like this. So I'm going to give you the actual, in this case also it'll be half t square e to the minus 3t. Okay, so this is we're just building intuition of what goes on. And what goes on, so one can keep doing this, but we don't want to keep doing this for every single number. We want to start actually pulling out, just like in the preferential attachment case, we want to pull out some kind of recursion relation, right? So what I'm going to do is make the general guess that C of k is some a k t to the power k minus 1 e to the power minus kt. Does that make sense? So we've seen in this case, the power of t is 1 less than that, and the power of the exponential is the same. So that's what I'm doing. And I want to pull out a relation here. So we're going to plug this in, and we're going to get the following recursion relation. So you will get k minus 1 ak half sum I j I plus j equals k. Oops. I ai I a j with a1 equals 1. Sorry, j. This should be j. Right? I mean, you can plug this in and see. You can plug this into that equation and you'll get this. So last time, I mean, you can see that so far, in a sense, our steps have been pretty much exactly like how we try to approach the master equation in the preferential attachment case. There it was a really simple recursion relation. We really, actually, I didn't even try to solve it. I just gave you the answer because it was fairly trivial. And if you sit down for 2 minutes with a pen and paper, you'll be able to do it. This is harder. This is not so obvious because of this product term, but clearly you can see that you can get all of them. Because you know what A1 is, you can put in the A1s and get A2. And using A1 and A2, you can get A3. And using A2 itself, you can get A4, and so on. So you can build up everything. So this is completely specified. This we should be able to solve, at least numerically, and know everything. But it would be nice to get it analytically, and actually you can get it analytically. So I want to give you a little sense of how this kind of calculation is done. The same thing can be done also, what I will describe now, can be done for the preferential attachment case, and more complex versions of the preferential attachment case. So in general, it's a rather general way of trying to solve the kinds of recursion relations. And some of you would have heard about this. How many of you have heard about generating functions? Right? So some of you know, and some of you don't. So let's, even for those of you who know, maybe it'll be good to sort of see it in action one more time. So for those of you who don't know, what we're going to do is define a function which will be a function of some other variable, let's say z, which I will define like this. K is equal to 1 to infinity, k a k e to the power k z. Okay, I'm defining this function like this. So g of z is this function. This is called a generating function. For those of you who have seen generating functions, you would have often seen things without this. This is the form that's more commonly seen. We're using a slightly different form precisely because of the structure of this recursion relation and because of the structure of the function we have. Okay? This turns out to be a convenient generating function, which will allow us to solve everything. So the point of a generating function is that if we can find this function, we can extract effectively all the AKs and all the moments of AKs and other kinds of things that you might want to know. And the way you do it is essentially by realizing that things like G of 0 is going to be this. Yeah? By realizing that dg, the derivative, is going to pull down another k. So you will have k squared, ak, e to the power kz. So if I evaluated this at 0, this would give me the second moment. So if one thinks of AKs as being some kind of histogram, some kind of distribution over the values k can take, then you can find all the moments rather simply if you know this function. Right? That's the purpose of a generating function. And the reason we work with this is that, as you will see in a moment, if we plug this in over there, we are going to get an equation for this that is a lot simpler than this one. This one is not so easy to write down an analytical closed form solution for AK right off the bat. But one may be able to do that if we use the generating function. Okay? So is it clear? Any question about this? Otherwise, I'll proceed to, let me come here. Actually, how much time do I have left? Because that thing is, there's a clock up. Okay, that's good. We have plenty of time. All right. So the way one does this is, of course, to take this equation and multiply both sides by k. Yeah, it's okay. I mean, not to worry too much. Multiply both sides by k, ak. Oh, sorry. Actually, I should be talking about this equation. We want to multiply both sides of this equation by k, and then sum over infinity. So I'm going to write that down. So sum over k, rather. So k minus 1, ak is half sum over k, sum over I, sum over j, with this condition that ij equals k. Ij minus sum over k. Oh, sorry, this is not there. I keep going back to that one. This is it, right? And I wanted to put in e to the kz. E to the kz. Right, so you see why I'm doing this. The left-hand side becomes sum over k, k squared, ak, e to the kz, minus sum over k, ak, e to the kz. So the left-hand side is from this kind of equation. Oh, I forgot. No, so I put in a k there. No, I do want a k because I'm defining the thing here. But what I did forget to do is multiply a k here. I should have done that. Yeah, you need the k because I'm defining the generating. Yeah. But on the left-hand side, I wanted a k because I don't know actually what the sum over ak is. The k minus 1, so I put in an extra k. So if I didn't put in the k, I would get k. I would get sum over k minus 1 ak e to the kz, but I don't know this term. So I am multiplying by k, and now I think I have done everything correctly. So there's a k squared term here, and the second term is a minus k. So let's just look at the left-hand side. The left-hand side, this we know. This is dg, this is the derivative, and this is just the generating function, right? So that's the left-hand side. Let's look at the right-hand side a little more carefully. So the right-hand side is now this. So here's a way to think about how to simplify this sum. Now we're summing over all I and j such that I plus j is equal to k, but we are also additionally summing over all k. So suppose I was actually, imagine the values of I and j I'm summing over. So without this sum, let's say this is 1, 2, 3, 4, etc. These are the values, right, of I, j we can take. So I need to try out this. These are the kinds of values, these integer values that I would be potentially looking at. These are the values that I, j would be able to take if there were no constraints. But in this sum, where I plus j is equal to 1, if k is equal to 1, that means I'm kind of looking at this line, right? This is the line k is equal, I plus j is equal to 1. This is the line I plus j is equal to 2. This is the line I plus j is equal to 3. So let me write that down. This is I plus j equals 1, I plus j equals 2, I plus j equals 3. So if I did not have this sum, and up here I was just looking at a particular value of k, let's say k equals 3, then I would be looking at this ij value, this ij value, and this ij value, right? Double sum just becomes a sum over these points. Is that clear? So sorry, this is, yeah, so this is I plus j is equal to 2. My apologies. This is I plus j equal to 3. This is I plus j equals 4. Right? So this is I is equal to 1, j is equal to 1. I plus j is equal to 2. This is I is equal to 2, j is equal to, sorry, j equals 2, I is equal to 1. So if I'm summing over only these points, I'm sticking to a particular I plus j value. That's exactly the constraint that one has here. But now what happens if I now also sum over all the k's? That means within this, I'm summing over this. Then I'm moving to the next line, summing over this and this. Then I'm jumping to the next line, summing over this, this, and this. If k goes from 1 to infinity, I'm effectively going to be touching all the points. So what I'm saying is that if you're summing over k, I, j with a constraint I plus j equals k, that's exactly the same as summing over all I and all j with no constraints. Exactly. So the other way to do it is put a Kronecker delta and then sum over all. Absolutely. So that's the other way to see it. But this is a more visual way of seeing it. So either way, essentially, we can take all this and write this down now in a more simple way and say this is going to be half, and now it'll sort of just split apart, right? So this is going to be sum over I, sum over j, and I plus j, I, j, ai, aj, e to the I plus j z. So what I've done is I've taken k inside here and just replaced it by I plus j. That's pretty much all I've done. So we're summing over I and j without the constraint now. All I, so this is greater than equal to 1, this is greater than equal to 1, and this is the case. Did I miss one? I brought the I plus j out from because of the k. And there's this I, there's this j, and this became the I plus j. Did I make a mistake? It's fine? All right, great. Sure. Sure. I mean, that's okay. I mean, these are all constants. So we're not so much worried about that. We're just worried about, this is just bookkeeping. From here to here, there's no problem. Huh? Oh, sorry. Oh, yeah, I guess, is it a minus? No, well, yeah, you can put a minus sign. That's not a big deal. If you want to really worry about convergence, you can put a minus sign. I've not said anything about Z, so yeah. So if you're worried about convergence, fair enough. I didn't really even think about that much because for me, this was just sort of just keeping track of each term and making sure all the terms are there. No, sure, you do have a, yeah, sure. So if you're worried about that, we can think of Z as negative to keep everything this thing. And then what we will be interested in is limits where Z goes to 0. Okay, in that kind of situation, then you need to just be careful that you're taking the limit from below in case there's a difference there. That's true, I never said anything about Z, so that saved me. All right. Okay, so now we are almost there. Let's just complete this. This is just, I mean, if you do split this up, you will see that it splits up rather easily. And you're going to get something like this. Ij, and you will get one term which will look something like I squared AI e to the I z. Don't confuse this with -1, the square root of -1. J aj e to the jz. And then there will be another term which will have half sum I ai e to the iz and j squared aj e to the jz. Right? So essentially I've split this apart, and then there's an I squared j term and a j squared I term. So let's write those down. The I squared AI terms, this will give you a derivative of G, and this will give you just G, right? Because there is no constraint here, now these are just, this is a product. So essentially we're going to get two terms that are identical and the half will go away. So let me write it down and you will get something like this. Okay, so anyone tell me if they're confused how we got this? Anybody have a problem with this one? The derivative comes from this and this. And you can see that the two terms are the same, so the half goes away. So overall, now you can see why it was useful to use this generating function. Because we use the generating function, this equation combined with this became rather simple. It became dg by dz minus g is equal to the right-hand side, which is g dg by dz. Right? Or just rearranging things a little bit. 1 minus g dg by dz is equal to g. Yeah? So now we're in a position to get a little closer to the solution. This seems a lot easier to solve, I'm sure you'll agree, than that. Yes? So that's the point of a generating function. You hopefully have a lot easier equations to solve than otherwise. This is a really useful trick. By the way, this bit about removing the constraints is also a very useful trick. It shows up all over the place. So keep that in mind also. It might be useful for you. Okay, now we need to solve this. So we're almost there. We need to solve this. And well, you can see. I mean, you know how to solve this. G is a function of Z. And this kind of equation you normally would be able to solve very easily. But you do, yeah. So exactly. So G is going to be, so you know what's going to happen. This is going to be 1 over G minus 1 dg is dz. And so you're going to have something like log G minus G, but there's a constant, right? So we need to know what this will be. So we need some limit of Z in which we have some handle on what G will actually be. And the only thing that we really know is A1. So we need to use that fact and get an initial condition effectively. So let me try and do that very quickly over here. Think about this. So I'm just writing out GZ. I'm actually expanding it out. So we have A1 e to the power Z plus 2A2 e to the power 2Z plus 3A3 e to the power 3Z. Is there a limit I can take in which the only thing that will survive is that term? Because we don't know what these are. We don't know what A2 is, we don't know what A3 is, but we do know this. We have kind of, we needed one initial condition. We have that from earlier. Is there a, what can I do to Z to get rid of every other term? Just take, how many different limits are there? Z equals 0, Z equals infinity, Z equals minus infinity. One of those should work. Yeah? So Z going to minus infinity, these terms will all go to 0 faster than the other terms. So as you take Z going to infinity, the only thing that can survive is this. And so G of Z, we know in this limit, without having reached infinity, but as it is approaching it, this has to approach e to the Z. Right? So we need to make sure that happens here, and that you can actually verify happens if this constant is 0. So the overall solution to this is this one, which I'm going to rewrite slightly as G e to the minus G is equal to e to the Z. Okay? So we've got quite far, but we have hit a snag. So this is the solution for the generating function. But as you can see, there are some transcendental elements, and we are not going to be able to write this down so easily in a closed form. Sorry, yes. What I did here, this should give me, if I was not mistaken, if I take the log on both sides, should be log G minus G equals Z. So I just exponentiated both sides. This was the solution we got, right? I used that to get rid of the constant of integration. So you can check that. If you want this to happen in that limit, you will basically and there was a constant, the constant just has to be 0. It's a boundary condition, or like an initial condition in this case, because it's just a single variable. Think of it as an initial condition at Z equals minus infinity, and then you get this. So this is our solution, and we are going to be slightly stuck here. Since there's not a lot of time left, I don't want to actually go through this. How do you actually solve this to get the AKs? But there is a way, and it's called the Lagrange, maybe I should write it somewhere big. Please look this up. It's called the Lagrange inversion formula. It's not magic, it's just a little contour integration. For those of you who know it, G is some kind of power series in AK. So AK, rather, is some kind of, in a series expansion of G, AK are the coefficients. And one way of extracting coefficients from some implicit equation like this is the Lagrange inversion formula. Essentially, it involves just a little contour integration. You think of Z as a complex variable, you do a little contour integral, you pull out the poles and residues, for those of you who have heard of that, and you can actually pull this out to give you the following very neat answer. So what you get after all this is K to the power K minus 2 upon k factorial. So there might be other ways in this specific case. Yeah. Yes. Yeah. So for those of you who know, there are these Lampard W functions. Okay, so this is just a sketch of how you go from here to here. We are going to skip it in the interest of time, but look up Lagrange's inversion formula, and you'll figure out how to do this. Here, it's actually remarkably simple, the solution. In other cases, it may not be. That's because this form was fairly simple. In other cases, in general, though, you might nevertheless be able to get some kind of implicit solution of this sort and be able to use the Lagrange formula to get some more complex things. But what does this now tell us about what we were interested in the beginning, which was the CKs? So I want to get rid of all this and spend the rest of the time telling you, let's investigate whether we understood what happened over here. So let's look at the CK now. The CK was AK t to the power k minus 1 e to the power minus kt, right? So that means CK is k minus 2 by k factorial e to the power k minus 1 e to the minus kt. Okay, I need Stirling's approximation again because we are going to ask what happens. So this is a distribution of the cluster sizes effectively, some kind of distribution of cluster sizes of different sizes, and we want to know what do the tails of these distributions look like. So I had sort of made some claim over here that distribution of sizes will be exponential, then it'll become a power law exactly at that point, and then after that something else. Well, who knows what it'll be. So let's try and get that, and that will be kind of enough for today. So to look at the tails of this distribution, I need Stirling's formula. So somebody tell me one more time Stirling's formula. I'll write the rest. K minus 2, k minus 1, e to the minus kt. Not the log form, but the right, very good. All right, so I'll put in some of the other things that one knows. 2 pi root k, yeah, and then there will be a k to the k, and then there'll be an e to the minus k that I'll throw up on that side. Sorry, it'll be e to the k, right? So it'll become minus k. No, plus k, right, all right, good, okay, so that's fine. Okay, so now you can already see this cancels out here, leaving a minus 2. So I'm going to simplify this, and I'm going to put k 5 by 2. Everyone agrees? There was a square root, and a k square came down there. And now we just have to investigate this thing. Okay, so think about this. Clearly, when t is some value which is not equal to 1, so look at t not equal to 1. When t not equal to 1, the large k limit of this is going to be an exponential drop-off. Correct? Everyone's happy with that? All the other things, I mean, there is an e to the k, but for anything that is where t is, well, okay, let me do one thing. Let me do the following. What we really want to look is in this region around t. So what we'll do is we'll take this function and do a Taylor expansion around t equals 1. That's the simplest thing to do, right? So we have, I'm going to just keep e to the k out here. We don't need to worry about that, right? Or shall I keep it in? I can keep it in. Let's keep it in. So we have e to the power minus kt plus k plus k minus 1 log of t. Okay, this is some function of t, which I want to expand around 1. So f of 1 in the first place is going to be e to the 0 plus k minus, when t goes to 0, sorry, t goes to 1, this is 0. So it's going to be just e to the k, right? That's why I wanted to get the e to the k out, but that's fine. Let's keep this. df by dt is what? Is f times minus k plus k minus 1 by t. And in the limit where this goes to 1, this is going to go away, and this is going to be minus 1, right? So it's going to be minus f of 1. And df, maybe it was better. I think my initial instinct of getting the k, e to the k out was actually better. So I'm going to redo this. So, yeah? Yes, yes. Oh, yes, okay. Sorry, thanks. So remember, the way we had started this all up was to throw in n by 2 links per unit time. And therefore, the average degree was going to grow as t. So essentially, what in this thing, I was actually writing this as k. What we've done is we've converted this into a kinetic problem, where actually, as time increases, you are going through different stages, and at different points in time, your average degree is exactly equal to t. So if what we are expecting to find here, thanks, sorry, I kind of missed making this connection to you more explicitly. What we're hoping to see from what I said earlier is that this is a function of time. This is some distribution that at every time there is a certain snapshot distribution. What I'm hoping to show you is that as time starts off below 1, you will get an exponentially decaying distribution. At exactly time t equals 1, you'll end up getting a power law, which will actually come from this. Okay? And as time goes larger than 1, you will again get an exponential distribution. Okay, since there's only 6 minutes, maybe we can leave some of these details away. Let me at least try to do the following. Let me try to convince you that at t equals 1, at this point, which is the same as average k equals 1, at that point, so the reason why all this is confusing, and sorry about the notation here, is because I'm using k here. So please don't get confused between this quantity, which is the average degree, and this k, which is the cluster size. I should have used something else. I should have used m or something. But having used this, remember, this is now saying how many clusters of size 1, how many clusters of size 2, 3, 4, etc. So this is a quantity that's taking various values. And t is what corresponds to the average degree. And as t increases, essentially we're looking at Erdos-Renyi networks of different average degrees. So you can kind of see the exponential decay that is coming there, and you can try to convince yourself that when t is not equal to 1, the exponential decay is what remains. And that's the main feature of this distribution. But put in t equals 1, and you'll find this exactly cancels this out, right? And what you're left with is this whole numerator is going to go to 1, and what you'll be left with is only this. So what you are left with, when t, which is equal to average k, is equal to 1, then ck1 basically is 1 over square root 2 pi k to the 5 by 2. So this is the characteristic that is very similar to what we've been talking about phase transitions. You have exponential size distributions away from the transition, and exactly at the transition point, you have a power law. What I have not shown you, and maybe I just have enough time to give you a hint of the idea, is what is this giant component that's coming here? And the way one studies the giant component is the following. Yeah. Yes. It has this power law distribution. Earlier and before it doesn't. It has an exponential distribution. So, to be a little more precise, over here, all clusters are finite and the distribution is exponential. Here, it is power law. Over here, remember, there is this one giant infinite cluster. But that giant infinite cluster doesn't cover the entire network. So what's left over, apart from that infinite cluster, are a bunch of finite clusters. And it's those finite clusters that have an exponential size distribution over here. So what you should think about of the Erdos-Renyi network in this k greater than 1 region is a giant component that covers a lot of nodes, but also some other disconnected smaller components. And those smaller finite size components will have an exponential distribution. Okay? Yeah. Oh, what was on the y-axis? Well, there were different things over here. What I was plotting were two curves. One curve was the fractional size of the giant component. Okay? And the other curve was the second moment of this size distribution. So let me be more precise. This, and that's exactly the point I'm coming to, this is 1 minus the first moment of the cluster distribution. This is the second moment. So the idea is the following, and I'll give you this intuition, and then you can try and, I will give you a reference where you can read more about this and actually understand how you get to understand the fact that there is a giant component in the first place. So think about this, this first moment. So the question is, what happens to k ck summed over k going from 1 to infinity? This is the first moment, right? And the second moment is this quantity, k equals 1 to infinity, k squared ck. So we are now asking the question, what happens to this quantity when t becomes larger than 1? So it turns out that when t is less than 1, basically m1 is always 1. And what I'm drawing here is 1 minus m1. That's why you basically see 0 all the way up to here. So imagine now, just imagine an infinite cluster. So suppose there is an infinite cluster. Remember, we're looking at the n going to infinity limit. So if there are finite clusters, they will all add up and show up in this sum m1. But suppose there really is an infinite cluster. Will it contribute to m1? That's the little tricky one key intuitive idea you have to get. And then you can understand why m1 is a very good way of understanding whether there is an infinite cluster or not. So you're summing over all k's, but you're summing over 1, 2, 3, 4, 5, 6. Those are all finite numbers. You are summing over all possible finite numbers, but a true infinite cluster will not show up in this sum. Right? So this is a little tricky. You have to go beyond thinking about finite. Your intuition about finite networks will mean this will always be 1. For a finite network of n nodes, however large, if you sum over all this, it will always be 1. But the true quantitative measure of whether an infinite cluster appears is if m1 turns out to be less than 1. Yeah. Yes. Sorry? Yeah. So this is C1 plus 2C2 plus 3C3 plus 4C4, etc. So think about this is all the nodes that are in one clusters, the total number of nodes in 2 clusters, right? Because every 2 cluster has 2 nodes. So each of the terms is the number of nodes that are there in those size clusters. Yeah. That was what? So that happened in this situation. So that was actually something we were actually getting from the finite. That's exactly the point. That normalization is something that you actually works and you think of, and it only works in the case where there are not an infinite cluster. So if everything is finite, then that is exactly the normalization and it works out. The case in which you get an infinite cluster is one that breaks that normalization. And that is really the interesting thing that happens over here. So the way you can actually, so you can get that from two things. You can actually take this solution we got and actually work out from this solution, in the case where t is larger than 1, you can actually try and work out this sum and see this. Or you can try and work it out from this generating function. Both are possible. And you can actually see, and you will find, if you do that calculation, that you will actually find that m remains 1 all the way up to t equals 1, and then actually starts falling below 1. So the physical interpretation of that really, it's exactly, that's the point. If you only think about finite networks, you think that's the normalization. There's no way it cannot be 1. And that's true, but it's true only as long as you have finite clusters. As soon as you get, so this is the little tricky thing. Since we are going to this infinite n limit, you have to change your intuition a little bit. And what you get by thinking about bigger and bigger and bigger finite clusters does not actually hold in the real limit where you go to n going to infinity. Yeah. Yeah. Well, one can always go the other way also. So there are other, so the real way to think about this is to also think about, when you think about phase transitions in general, it's not just the n equals infinite limit that tells you about the transition, but there's this entire field which some of you may have heard about, which is about the finite size scaling. So what happens to the same transition when you are in a finite system, and how do these things actually head towards those discontinuities in the infinite system. So people have taken this, we don't have time to go through that, but people have looked at this whole thing purely in the finite case, and then taking the limit and looking at how various things scale. So in particular, you know that one of the things that will happen is this value will sort of smear out. And it smears out over a certain region that scales in a certain way with n. And so you can actually do a lot of these calculations in finite n, where all the physical interpretations work out, but they're much more complicated. And then you can get the entire finite size scaling theory for this phase transition and see that the interpretation works out as you go to n going to infinity. Okay? So you're not wrong that in some ways it seems like we have pulled a trick out of the bag. Okay? But in this case, I think it's fair to say that we do have a fairly solid understanding that this is a real physical phenomenon. And this mathematical trick and the normalization issues are not an artifact of that. And I think the best way, I don't know if you can, the best way is that, right, correct, yes, absolutely. So really, So really what's happening is exactly in this region, you are ending up getting a delta function, which then goes off to infinity. Correct. But your point is not, it's a valid thing to think about. Your question is a perfectly valid one. There is, at this level at which I've told you, it does seem like a little bit of trickery. Okay, maybe we should wrap up a bit because we shouldn't go too much over time, but I'm here for the tutorial, so maybe we... Thank you.